Hi, so today we're going to be looking at the functional group amides, and right now we're going to be looking at their general equation as well as their general structure. So the general equation for an amide is RCON R prime R prime prime. Now remember that the R's can replace any carbonyl group. So let's look at the general structure of an amide. So basically what you have is a nitrogen atom that's connected to our carbonyl group, which is a carbon double bonded to an oxygen. To that carbon, we have our first R, and on the nitrogen, we have R prime as well as R prime prime. And it looks just like that. Alright, so next what I'm going to teach you is how to name amides. So here I have two examples laid out, and let's try and name this first one. What you first want to do is look for any side chains. So we have two side chains that are connected to the N, and since there's two of them, sort of like the same as the locator number, we have to put N, N. And since they're both methyl chains and there's two of them, it's going to be dimethyl. Then we have to name the parent chain, and the parent chain is always the one that's connected to the carbonyl group, and you have to make sure you count that carbonyl carbon. So here we have 1, 2, 3, 4 carbons. And so now we have 4 carbons that would imply butane. So what we'd put is butan. And since it's an amide, we have to add the amide ending. So this molecule is NN dimethyl butanamide. So here's our next example. We look for any side chains. So we see that we have one here and one here. And like in the example above, you have to start counting your parent chain at the first carbonyl carbon. So 1, 2, 3, 4. This methyl chain is on the second carbon, and this methyl chain is on the N. So this will start off as N, comma 2, and since there's two chains, it's going to be dimethyl. And we see that we have 4 carbons again, like above. And since it's an amide, we have to add the amide ending. So this molecule is N2 dimethyl butanamide. So next we're going to be looking at the properties of amides. At first we're going to be looking at the intermolecular forces. So here we see that amides have dipole-dipole interactions. You can see here that there's a partial positive at the nitrogen atom and a partial negative at the oxygen atom. And we see that these two dotted lines represent the dipole-dipole interactions between amides. The O negative is attracted to the N positive. This O negative is attracted to this N positive. There are also hydrogen bonds present in amides, as we can see here in amides that are relatively smaller and don't have a carbonyl change at this N as it could. If it had a hydrogen, that hydrogen could potentially have a hydrogen bond with the oxygen on another molecule, because oxygen has 2 sets of lone pairs. Next we're going to be looking at the solubility of amides. Now typically amides are insoluble, however some of the smaller amides can be soluble. As you can see here, a smaller amide will have a dipolar nature, where there's a dipole between the oxygen and the carbon and the nitrogen and the hydrogen. This allows for potential H bonds with this oxygen up here and this nitrogen down here, which makes smaller amides have slight solubility. However, if this H were to be replaced with an alkyl chain, and the longer they get, the less soluble they become. Next we're going to be looking at the melting points and boiling points of amides. Now amides have one of the highest boiling points out of most of the other functional groups, and they're much higher than their parent hydrocarbons. As we can see here, the high boiling point and melting points are due to the hydrogen bonding that occurs. And this typically happens in primary amides, which means that the nitrogen has 2 hydrogens instead of a carbon chain. As we can see here, the hydrogen has a partial positive and the oxygen is more electronegative, and it has 2 sets of lone pairs, which allows for hydrogen bonding. So next we're going to look at the reactivity patterns and trends of amides. Now amides are typically the least reactive of all the functional groups. And the reason why is because nitrogen sort of donates its lone pair to the carbonyl group, as well as the fact that R prime and R prime prime usually block the advance of attacking electrophiles to this lone pair of electrons. Next we're going to be looking at reactions that create amides. Now amides are created through a process called condensation, where typically a carboxylic acid combines with an amide as well as some heat produces H2O and the amide. So here we have a sample reaction. We have 3-methylbutanoic acid and ethylmethylamine. So here we see that the 3-methylbutanoic acid has an OH group and the amine has a hydrogen. Now these are going to break off the functional groups and form water, as well as our amide, N-ethyl, N3-dimethylbutanamide. As we can see, our ethyl chain is here on the N, and our 2 methyl chains are on the N as well, and the 3rd carbon. Although amides go through a variety of reactions, amides typically, as a reagent, will just go through the reverse, which is called hydrolysis, where an amide recombines with water and splits up to create the carboxylic acid and the amide that was used before. And typically the conditions have to be either acidic or basic.